I'm going to record this session today. So I guess that before we move on, or before we start looking at sequences, which is the last thing we're going to look at before we take a test. So on Wednesday, I'll be in Lee County on Wednesday, but I'll be broadcasting, I guess, over to Wolf as well, and we'll look at at the study guide for the first test. And then my idea is that you will take your test either Thursday or Friday, or if we need to take it that next week, that's okay too. Um, so what I'll do is I'll leave the test with, or I'll send the test to like the contact person at the school, and then you can make arrangements to take that, and then I'll come back and pick it up. But anyway, so let me show you a couple things. I'm going to try to share my screen. I tried to the other day, but it didn't work out that well. But I think I figured it out. So I'm going to try to share the screen here, and I'm going to show you a couple things. Okay, James, can you see my screen? Okay. All right. So I want to show you a couple things on, well, not a couple, just one thing on MyOpenMath. So when you go into MyOpenMath and you click, so here's the homepage, and you click on our class, underneath course documents and resources, I've added a new section. It's in green. It says test study guides. So this is where the study guides will be. And so if I click on study guide 1, I can open it. And one thing I wanted to tell you is that this study, so I'm going to enable editing, I guess. So this study guide looks exactly like the test. The test doesn't have the same questions on it exactly, but the questions are the same type of question. So for question 1 on the study guide, it's a multiple choice question. It asks which of the following, and that should say numbers, which of the following numbers is divisible by 3 and 5 but not by 2? And then it asks you to choose there. So the first question on the test will be just like this. So it may have different numbers here. It'll have different choices, but it'll be the same type of question. Then on the test, you'll have a group of numbers that you're asked to put in the boxes to show what number system they belong to, just like you do on the study guide. So the study guide is a lot like the test. So take a look at that study guide, and we will go over it and answer any questions about it next time in class on Wednesday. So that's the actual study guide, and that's where you find it in MyOpenMath. You can also find it in Blackboard, and you can click on, if you're in Blackboard, you can click on the menu over here, right underneath syllabus and introductory documents, you'll see test study guides. And when you click on test study guides, it will bring up that first study guide for you. All right, how does that sound? Does that sound okay? Oh, wait a minute. So I'm going to stop. Okay, I'm going to stop sharing my screen, and I'm going to share the sequences information sheet with you. Now you have this information sheet as well, so we're going to look at as much of this as we can before time runs out. But let's take a look at this. So this is the last topic that we're going to study in number theory. And believe it or not, when we start talking about growth, which we will do next week, and modeling growth, some of this information about sequences will come into play again. So let's talk a little bit about sequences. So a sequence is a list of numbers related to each other by a rule or a pattern. So each number in the list is called a term. So basically a sequence is just a list of numbers, and if you have only part of a sequence, you can find the next terms because they follow a certain pattern. So I'm looking at the following sequences here, and let's see if we can first of all determine the pattern or the rule and then find the next three terms of the sequence. So I'm looking at 2, 4, 6, 8. And actually, these are just the even numbers. So what's the pattern? Well, the pattern is that we just have the even numbers. So I'm going to say even numbers. But also, and excuse my writing again with my mouse, but also there's another way that I can think about this. This is just a list of the even natural numbers, actually, so maybe I should have said even natural numbers. I'll say even nat numbers. But there's another way I can think about this. Notice that to get from 2 to 4, I have to add 2, right? And to get from 4 to 6, I have to add 2. And to get from 6 to 8, I have to add 2. So in this sequence, we can describe this sequence sort of generally as the even natural numbers. But we can also say that to go from one term to the next term, you need to add 2. So we can also say that the rule here is add 2. All right? So to get from one number to the next, we add 2, and then I can easily think of the next three terms. The next three terms are 10, 12, and 14. And then it'll continue on. All right, so that's the idea behind a sequence. Well, let's look at the next sequence that we have here. The next sequence is 3, -3, 3, -3, 3. So basically here the pattern is we're just alternating between -3 and 3, right? So alternating, so alternate, I'll say alt between -3 and -3. So alternate between 3 and -3. But there's another way that we can think about this sequence. We can think about it as multiplying the previous term by -1, right? So if I multiply 3 by -1, then 3 times -1 is -3. And then if I multiply -3 by -1, so times -1, -3 times -1 is 3. And then if I multiply 3 by -1, I get -3. -3 by -1, I get 3. So another way we can think about this pattern is to multiply by -1. So if you have one term, the way to get to the next term in this sequence is you just multiply by -1. So we can easily list the next three terms, -3, comma 3, comma -3. And then it goes on from there. So the reason why I like to show that example is because a sequence of numbers, it doesn't have to increase. In fact, it can decrease, or they can alternate in value, the numbers can. So, there are different ways that we can have different sequences. Let's look at this last sequence. So I'm looking at the sequence and I notice that it's 1, 4, 9, 16. And in the interest of time, I'll just go ahead and tell you that I'm sure you can figure it out if you looked at it, but this is basically just taking the natural numbers and finding the square. So it's a list of the squares of natural numbers. So I'm just going to say squares here. So 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared. So the next three terms are going to be 5 squared, or 25, 6 squared, or 36, and 7 squared, or 49. And then that will continue on. Now, one of the things I want you to notice is that there's also something very different, or very neat, not different, but neat about these numbers. If I were to add something to 1 to get to 4, what would that be? Well, that would be 3, right? So 1 plus 3 is 4. If I were to add something to 4 to get to 9, that would be 5. So 1 plus 3 is 4. 4 plus 5 is 9. 9 plus what is 16? Well, that's 7. 16 plus 9 is 25. 25 plus 11 is 36. And 36 plus 13 is 49. So notice that looks like a B, but it's really a 13. So notice that to get to the next number in this sequence, you add the next highest odd number. So if I wanted to get from 49 to the next number in the sequence, I would add the next highest odd number. And the next highest odd number is, what, 3, 5, 7, 9, 11, 13, 15. And what is 49 plus 15? Well, that's 64, right? So 64 would be 8 squared, or the next number in the sequence. So that's something very neat about the sequence of perfect squares. To get from one perfect square to the next, you just add the next odd number. I think that's pretty neat. All right, so that's the idea behind sequences. Just a list of numbers. They relate to each other in a certain way. So one famous sequence that is studied, and that should be studied, so one famous sequence studied by number theorists is the Fibonacci sequence. Although it was first written about by Indian prosodist, and a prosodist, I guess, is just a guy or a person who studies language and how words are arranged. So there was a prosodist and mathematician in the 6th century named Virabhanka, I guess, I don't know. So he was an Indian mathematician, and he wrote about the Fibonacci sequence. He didn't call it the Fibonacci sequence, but he wrote about this sequence of numbers. The reason why we call it the Fibonacci sequence is because in 12012, in his book Liber Abace, or Abace, Leonardo Fibonacci used the sequence to solve what he called the rabbit problem. And if you want to look at a couple of the optional videos, they go into depth about the Fibonacci sequence, and they'll explain what the rabbit problem is and how Fibonacci used this sequence in his book. So what is the Fibonacci sequence? Well, it's actually a pretty neat sequence, and it's pretty easy to develop. And it's very simple to develop, but it has some interesting properties. It says the first two terms of the Fibonacci sequence are 1 and 1. The other terms are found by adding the two previous terms. So notice here I have 2. Well, 2 is 1 plus 1. 3 is 1 plus 2. 5 is 2 plus 3. 8 is 3 plus 5. 13 is 5 plus 8. So in order to get any term in the Fibonacci sequence, you add the previous two terms. So to get 21, I'm going to say 8 plus 13. To get 34, I'm going to say 13 plus 21. And to get 55, I'm going to say 21 plus 34. So what are the next three terms of the Fibonacci sequence? So if you go back to our previous page, the last two terms that we looked at were 34 and 55. So if I add 34 and 55, I get 34 and 55 is 89, right? So that's 89. Now, 55 plus 89 then is 144. And 89 plus 144 is 233. So those are the next three terms of the Fibonacci sequence. Excuse me, sorry about that. And you just get those terms by adding the two previous terms. All right, in a sequence, we usually label the terms using a lowercase a with a subscript indicating that term's position in the sequence. So a sub 1, we say, is the first term, a sub 2 is the second term, and so on. In general, we refer to the nth term in a sequence as a sub n. So in the Fibonacci sequence, we could say a sub 1 is 1, a sub 2 is 1, a sub 3 is 2, a sub 4 is 3, and a sub 5 is 5. And in general, the way that you get a sub n is by taking a sub n minus 1, so the term right before n, and then the term right before that, a sub n minus 2, and adding them together. So that's how you might get the Fibonacci sequence if you wanted to express it generally. Sometimes we can actually find a formula for a sub n, and this gives us a way to find any term of the sequence without needing to write all the previous terms, so all the terms that come before it. So let's consider that sequence 2, 4, 6, 8, 10. We can represent the nth term of this sequence using the formula a sub n equals 2n, right? Because if 2 is a sub 1, then 1 times 2 is 2. And 4 is a sub 2, and 2 times 2 is 4, and so on. So if we want to find the third term in the sequence, we just evaluate a sub n for equals 2n for n equals 3. So if I want to find a sub 3, which will be the third term, we already know what it is. We know that it's 6. But if I take this formula and put 3 in for n, then I find 6. Because 2 times 3 is 6. And we see that the third term is 6. But we knew that already. But what if I ask you to find the 17th term in the sequence? Well, we could count 2, 4, 6, 8, 10, 12, and so on 17 times. Or we could use this formula, a sub n, equals 2n, to help us find the 17th term. So what we're doing here is we're actually looking for a sub 17, and that's just going to be 2 times 17. And 2 times 17 happens to be 34. So if you have a formula for the general term of a sequence, then you can find the terms rather easily. I'm sorry, I don't know why I'm yawning. I'm not bored. Maybe tired. Consider the following general term for a sequence. A sub n is equal to 3 over 2n minus 1. And it says find the first 5 terms of this sequence. So what I need to find is a sub 1, a sub 2, a sub 3, and so on, right? A sub 4, and a sub 5. So I'm going to find that by just taking whatever the sub number is. So this is a sub 1, and I'm going to replace it with n in this formula, or replace it for n in this formula. So a sub 1 really is equal to 3 over 2 times 1 minus 1. And when I simplify that, I get 2 times 1 is 2. 2 minus 1 is 1, so I have 3 over 1, and that's just 3. If you have a graphing calculator or a calculator that will, that will do several calculations, you could type this in and it'll just do it for you. If I wanted to find a sub 2, then I'm going to put, instead of 1 where n is, I'm going to put 2. So I have 3 over 2 times 2 minus 1. So 2 times 2 is 4, and 4 minus 1 is 3, and so 3 divided by 3 is 1. So a sub 2 is 1. And I could go on. So a sub 3 is going to be 3 over 2 So 2 times 3 is 6, and 6 minus 1 is 5, so this one ends up being 3/5. So far my sequence is 3, 1, 3/5. And if you find a sub 4 the same way, you're going to get 3/7. And if you find a sub 5 that way, you're going to get 3/9. And 3/9 will reduce to 1/3. So this is quite an interesting looking sequence. And we probably at first glance, if we just saw a list of the terms of this sequence, we probably wouldn't be able to just at first glance know what the pattern is. We'd have to do a little bit of thinking first. But the sequence is 3, 1, 3/5, 3/7, 1/3. And then if you wanted to find a sub 6 and so on, you could. All right. Excellent. So you may have some homework problems that ask you to come up with the first terms of a sequence given the formula. So we have a couple types of sequences that we're going to talk about. The first one is an arithmetic sequence. It comes from the word arithmetic. And a sequence where a constant amount is added. So the important word here is added. So a sequence where a constant amount is added to the previous term to get the next one is called an arithmetic sequence. Arithmetic. So the constant amount added is called the common difference. So in our first example, if we can go back to, in our first example, remember we said that if I take 2 and add 2 to it, I get 4. If I take 4 and add 2 to it, I get 6. This is an arithmetic sequence. And it's an arithmetic sequence because I add a constant amount to the previous number to get the next number. And that constant amount that I added was 2, so 2 is the common difference. This is not, even though I add something, this is not an arithmetic sequence because the amount that I'm adding increases every time. It's the next odd number. So it's not constant. So that's not arithmetic, but the top one is. So let's look at this graph. It says this graph shows the amount of money in billions that American pet owners spent on their pets from 2001 to 2007. Notice the amount of spending increased by a constant amount each year. According to the graph, each year Americans spent $2 billion more on pets than in the previous year. So these numbers represent an arithmetic sequence with a common difference of 2. So 29 plus 2 is 31, 31 plus 2 is 33, 33 plus 2 is 35, and so on. So the first question is, if this trend continued, how much would Americans have spent on their pets in the next 3 years? So 2008, 2009, and 2010. Well, I know that the common difference is 2, so that's the amount that I add to a previous term to get the next one. So all I have to do is add 2 to 41. So 41 plus 2 is 43. So in 2008, Americans would have spent 43 billion. In 2009, I'm going to take 43 and add 2 to it. So Americans would have spent 45 billion. And in 2010, I'm going to just take 45, the previous number, and add 2 to that. So that's 47 billion. So we can find the common difference. We were told that this common difference was 2, but we can find the common difference of an arithmetic sequence by subtracting any term from the term that directly follows it. So here, if I didn't know this common difference was 2, I could take 33 and 35, and I could take 33 and subtract it from 35, or 35, sorry, and subtract 33 is what I want to do. So I take any term and subtract it from the term that follows it. So 35 minus 33, and that is 2, and the common difference is 2. So if you know the first term and the common difference of an arithmetic sequence, you can find a formula for the nth term by using the following. You take the first term and you multiply that by you add that to the product of n minus 1 and the common difference. So, for example, let's look at this question here. It says the first term of a certain arithmetic sequence is 6, and the common difference is 4. We want to first write the first 5 terms of the sequence. Second, we want to find a formula for a sub n. And then third, we want to use that formula to find the 20th and 100th terms in the sequence. So if I know that the first term in the sequence is 6, then 6 is a sub 1, right? But I want to find 4 other terms. Well, I know the common difference is 4, and if you remember, the common difference is what we add to a previous term to get the next one. So I know that the next term is going to be the previous term 6 plus 4. So the second term in this case is 10. Now I'm going to take 10 and add 4 to it. So the third term in this sequence is 14. I'm going to take 14 and add 4 to that. 1, 2, 3. So the fourth term will be 18. And if I take 18 and add 4 to that, then the fifth term in the sequence is 22. So 6, 10, 14, 18, 22. It will be this sequence. And we could, if we wanted to, find other terms, but it just asks us to find the first 5. So 6, 10, 14, 18, 22. 5. All right. So now it asks us to write a formula for a sub n. So a sub n, remember, is equal to a sub 1 plus the common difference times n minus 1. So a sub 1, I know in this case, is 6. Plus the common difference I know is 4. Times n minus 1. Now I can use the distributive property here to simplify this a little bit. So I have 6 plus 4 times n is 4n. And 4 times negative 1 is negative 4. And then I can combine like terms. 6 minus 4 is 2. So a sub n has the formula 2 plus 4n. Or 4n plus 2, doesn't matter, either way. So this is the formula a sub n. Now I can use this to find the 20th term in the sequence and the 100th. So let's find the 100th because we're running out of time a little bit and I want to be able to talk about the next type of sequence. So we'll find the 100th term. All I have to do is put in 100 for n. So the 100th term is a sub 100, and that's equal to 2 plus 4 times 100. And when I work all that out, 4 times 100 is 400, plus 2, I'm going to get 402. So 402 will be the 100th term in that sequence. All right. All right, let's talk about another type of sequence. The other type of sequence that I want to talk about is a geometric sequence. And the geometric sequence is a sequence where each term after the first is obtained by multiplying the preceding term by a constant amount. Not equal to 0, of course. And the constant amount that is multiplied is called the common ratio r. So really that second term, 3, negative 3, 3, negative 3, that is a geometric sequence, and the constant ratio that I multiply each time is negative 1, right? So the common ratio for a geometric sequence can be found by dividing any term in the sequence, other than the first term, by the term that precedes it. So if you take any term a sub n, just divide that by the term that comes before it. If you know the first term of a geometric sequence, a sub 1, and the common ratio r, you can find a formula for the nth term by using the following. So a sub n is going to be equal to a sub 1 times r to the n minus 1. So let's look at this example here. It says, consider the following table showing the population of the United States in 2000 and 2010 with estimates given by the Census Bureau for 2001 through 2009. All right, so the first thing that it asks you to do is to show that the population is increasing geometrically. If I want to show that this is increasing geometrically, all I have to do is find a common ratio. Find a common number that each term is multiplied by. So I'm just going to take a couple. You could do as many of these as you like. I'll take a couple. A sub n's over a sub n minus 1. And see if I get the same number. Now, if you take a couple of these pairs of numbers and divide them and you don't get the same ratio, then this is not a geometric sequence, okay? So let's take a look first at, I guess, just 2000 and 2001. So I'm going to take the population for 2001, 284, and divide it by 281.4, the population for 2000. And when I do that, I get approximately 1.009. All right, let me try something else. Let me try 2002 and 2001. So 2002 is 286.6, and I want to divide by 284.0. And when I divide, I get approximately, I need to make these wavy. So I get approximately 1.009. And you'll find that if you divide 289.3 divided by 286.6, you'll get 1.009. If you divide 292 divided by 289.3, you'll get 1.009. So this is increasing by a constant amount. So to get from 181.4 to get from 281.4 to get to 284, I do multiply by 1.009. To get from 284 to 286.6, I multiply by 1.009. So this is, in fact, a geometric sequence. All right, so find a formula for the general term. Well, the general term is going to be a sub n, and it's equal to a sub 1, which in our case is 281.4 times 1.009, which is the common ratio r, raised to the n minus 1. Now, this formula does not look at raised to the n minus 1. So this formula does not look as nice and neat as the formula for an arithmetic sequence, but it's still useful nonetheless. The next question I have says, to use the formula to project the U.S. population for the year 2020. So let's think of what n goes along with the year 2020. Think about this. 2000, the year 2000 is n equals 1. So this is n equals 1. This is n equals 2. This is n equals 3. This is n equals 4. This is n equals 5, and so on. So 2020 is going to be n equals 21, right? Because we start with 2000 is our first. So in order to get to what n is, you take the last 2 digits of the year and just add 1 onto that. So 2010 is actually n equals 11. So 5, 6, 7, 8, 9, 10, 11. So 2020 will be n equals 21. So all I have to do to find the formula or find the population for the year 2020 is put n equals 21 into this formula. So I have a to the 21st, or the 21st number in this sequence, is 281.4 times 1.009 to the 21 minus 1. And when I do that, here's how I would do that. So I have 281, sorry, 0.4. So I have 281.4 times 1.009 raised to the really the 20th power, right? So on your calculator, this is how I would do it. I would first of all take 1.009 and raise it to the 20th power, and then I would multiply by 281.4. And when you do that, you get 336.6. So 336.6. So that means that the U.S. population in the year 2020 will be 336.6 million people if the trend continues. All right, so we have a couple more problems to take a look at, and I think we might be able to get them all finished before 10:06. I don't know, but if not, well, actually we have 3 more. But if not, then I think you have enough that you'll be able to do the homework on sequences. And remember to take a look at that study guide, and I'll answer questions about the study guide next time in class on Wednesday. So let's look at this next problem. It says, consider the following geometric sequence: 1, 5, 25, 125, 625, ... Find the common ratio of the sequence and find a formula for a general term. So the common ratio, you could probably see this without doing any sort of division. But in this case, the common ratio is just taking the previous number and multiplying it by 5. So the common ratio is 5 in this case. So 1 times 5 is 5, 5 times 5 is 25, and so on. For some of them, it'll be difficult to see, or it won't be as apparent. So what you can do is just pick any 2 numbers in the sequence. So I'll take 125 and 25 and just divide those. So I'm going to say 125 divided by 5. I'm sorry, 25 is 5. I could take 1 and 5, right? 5 divided by 1 is 5. 625 divided by 125 is 5. So the common ratio R is 5. Now, I know the first term, 1, and I know the common ratio, so all I have to do is fill in A sub n is equal to A sub 1 times R raised to the n minus 1. So A sub n in this case is going to be 1 times 5 raised to the n minus 1. Well, 1 times anything is just that something, so in this case we can simplify this a little bit to say A sub n is equal to 5 raised to the n minus 1. So let's look. I think we have time for, we have about 6 minutes left. I think we have time for one more. And then take a look at this last one, and if you have questions about it, I can answer those next time in class. So it says, write the first 5 terms of the geometric sequence with first term 6 and common ratio 3, or I'm sorry, 1/3, then find a formula for the nth term. So the first 5 terms, so the first term is 6, the second term is 6 times 1/3, so 6 times 1/3 is 2. The third term is 2 times 1/3. That's 2/3. Sorry about if you keep hearing that noise. I'm getting emails. And then 1, 2, 3. The fourth term is 2/3 times 1/3, and that is equal to 2/9. And the fifth term is 2/9 times 1/3, and that is equal to 2/27, right? So 6, 2, 2/3, 2/9, 2/27. So what is the common? Oh, we know the common ratio is 1/3. So now let's find a formula for the nth term. So that's a sub n is equal to 6 is the first term times 1/3 raised to the n minus 1. And I could have found this first because I knew the first term in the common ratio, and then put 1n for n, 2n for n, 3n, 3 for n, 4 for n, and 5 for n, and found these terms that way. But that is the general or the n term of the sequence. Well, I mean, I have another question here. I mean, we have some time. Let's see how far we can get with this one. So it says for the general geometric sequence 5, 50, 500, 5,000, we want to find a formula for a sub n. So we need the first term, that's 5. We also need the common difference. I don't have the common difference, but I can find it by choosing any two terms and dividing. So 500 divided by 50 is equal to, when I divide 500 by 50, I get 10. So the common difference is 10. When I divide 50 by 5, I get 10. When I divide 5,000 by 500, I get 10. So the common difference is 10. So a formula for the general term, or the nth term, is a sub n is equal to 5 times 10 to the n minus 1. And now I can find the 10th term by saying a sub 10 is equal to 5 times 10 to the 10 minus 1 power. So that's really 5 times 10 to the 9th. And 10 to the 9th is 1 followed by 9 zeros. And 5 times that is 5 followed by 9 zeros. So that is the 10th number in that sequence. Well, we've got about 2 minutes to go before 10:06. Do you have any questions, James, at all? All right. Well, if you do, just email me or give me a call, or save those for next time, and we'll talk about these in class. So next time in class, we will look at the study guide for the test, and then later this week, you'll be able to get that test out of the way, and we'll move on to growth in Chapter 2. All right, so I'm going to sign off here. It's almost 10:06, and I guess I will talk to you on Wednesday.